time for... Okay, yeah, so that was a wonderful starting talk, and now we're really happy. I'm really happy to have Paola Iannone speaking. Hi, Paola. And she's going to be talking about how we're going to be teaching mathematics using interactive theorem provers and transitioning into university. Thank you.
Oh, thank you. Thank you for having me. It's always a pleasure to talk after Kevin, because Kevin is the reason why I got into this, thinking about using interactive theorem provers for teaching mathematics, but not only, as we will see at the end of the talk. So I'm Paola Iannone, I work at the University of Edinburgh, and when I give talks like this, I always say I'm a social science researcher that knows a little bit more mathematics than your standard social science researcher. So what will I do today? Ouch, where do I do that? Oh no, now we have the scenario that my clicker doesn't work. Ah, there you are. So when I started to prepare this talk, I took this occasion to really try to summarize what are people doing regarding this idea that we may use interactive theorem provers for teaching undergraduate mathematics, for teaching first year mathematics, as Kevin was doing in 2018, or for teaching about interactive theorem provers to undergraduates so that they may use one day this in their research. So in order to do so in this talk, I want to talk about, first of all, why do we want to teach interactive theorem provers? Why do we want to teach them to first-year mathematics students? After all, if you think about how we teach first-year mathematics students, this is fairly traditional. So there is still a lot of using chalkboards and a lot of presenting mathematics as something which is complete and something which is very, very well organized and always precisely written. So why do we want to change all this, and why do we want to use interactive theorem provers, and what happens if we do use interactive theorem provers? Oops, sorry, doing that. There is not only one interactive theorem provers. There are, in my mind, at least 3 different types of interactive theorem prover that can be used. So I will talk a little bit about what these are, just to say the different types that there are. I will talk a little bit about lean in the classroom, and I was asked by a referee of one of my papers once, why do you focus on lean? And I didn't really have an answer to this, apart from the fact that this is what seems to be used quite a lot at the moment, and this is where I started. But lean is one of the interactive theorem provers that is used the most for teaching for now. I want to talk about how students engage with lean, and we have some theoretical tools in education that we can use to do that. I'm not going to talk very much about the theoretical bits, but I am going to talk about a little bit about the outcomes of these studies. I want to talk very quickly about resource design and evaluation, and this is something that is happening quite quickly. So there is a lot of colleagues who are designing resources for teaching mathematics with lean. But what is needed at the moment is a serious pedagogical evaluation. So I designed this fantastic set of tasks for students. How do these contribute to the teaching and learning of these students' mathematics? And then I want to talk about types of knowledge to successfully interact with lean. And this is my, if you like, is the work of my PhD students, whom I'm hoping is in the audience today, so she can help me. And this is a little bit like the more abstract bit, and this answers the questions, what do I need to know in order to be able to be good at using lean? This question is interesting for reasons that we will see later, and it's also quite complex. I'm sorry about that. I don't really know why. Okay, but it's also quite complex. And then I want to have 5 minutes on what we are doing next. So this is the plan of the talk, and thank you for having me. This has been really good for me to try to understand what I want to do next and what needs to be done next. Anyway, so why theorem provers? A lot of the teaching in general of mathematics has been supported by technology at the moment. Part of my research interest was the use of technology in teaching university mathematics. And this, up to the use of theorem provers, still has kind of presented itself as the use of technology for summative assessment of mathematics. So computer-aided systems and so on. So when I was introduced to this idea that we could use these things called interactive theorem provers to teach first-year mathematics, I thought, well, this brings together two of my research interests, the research interest in mathematical reasoning and the research interest in using technology. So I think that there is a lot of movement at the moment to try and support this idea that we want to really use some technology, and then if you want to use some technology, why not this technology to teach pure mathematics to, for example, first-year students. Gilana and her collaborators, Larvor and Jan, make a very good case in this paper for why we did need to introduce technology in the teaching of proof. And one of the points that they flag up is that at the moment we teach mathematics in a way that has nothing to do with the process of doing mathematics. And this is a problem for the students. So we teach mathematics as this fantastically completed body of knowledge, and the students don't ever see what happens under the bonnet. So if the research mathematics is going towards the direction of using more and more interactive theorem provers, but also generative AI, then we need to bring these tools into the classroom so that the students may have, at some point, perhaps the possibility of looking what happens under the bonnet. So this is the general justification from the pedagogical viewpoint of why we would like to use interactive theorem provers. There is also a research justification. I thought it was great to hear Kevin saying, and I want to understand what I need to do, therefore I gave a lecture course. And so this kind of joining research with interactive theorem provers and teaching, I think, is something that mathematicians are also quite interested in and quite willing to do. So there are at least, as I said before, there are at least 3 different types of interactive theorem provers. So 3 types, I think, as different. So there are systems that have been developed for mathematics research and formalization, and these are the things like Lin, like Rock, like Isabel. And these were developed first with the idea of formalization. Nobody was really thinking about teaching when these things were put together. I don't think that this was anywhere in the landscape of the 60s where Automat was first put together and Eindhoven. So these are really tools that have come out from mathematicians to say, okay, let's try to see whether it is possible to have a system that can check my proofs and formalize my results. And this is how I think it started and how it's been used for a very long time. And now, of course, there is the possibility of auto-formalization. So this all sits in the side, if you like, of mathematics research. There are systems that have been developed bespoke for teaching, and these are systems like Lurch, like Educara, and these are really not interactive theorem provers in the sense that Lin is. They have been designed and taught with kind of teaching in the minds, and they have different kind of characteristics and different things as the systems can do. And then there are ITPs that use controlled natural language, and Patrick is going to talk about Lin verbose on Friday, I imagine, but there is another system called Waterproof, which has been developed in Eindhoven. And these systems are really interesting because one of the issues with Lin, as we will see, not one of the issues, one of the characteristics of Lin, as we will see later on in this talk, is that the students is doing this programming activity, so they are inputting line of codes in this system, and this kind of doesn't really represent well what the students would do if they were to prove the same result on pen and paper, which can be a benefit for some reason, but a disadvantage for the other. System like Lin verbose, which is, I have an example on the on the screen, but as I said, Patrick will talk a lot more about this on Friday, allow the students to write more or less in the same way in which they would write the proof if they were writing on pen and paper. So they have been constructed with an interactive theorem prover underneath. I think Lin verbose has got Lin underneath, while Waterproof has got a Rock, so that the students wouldn't write coding lines or things that looked to them like coding lines, but they could write kind of text, if you like. Most of my research has been into working with using Lin in the classroom. And as I said, this has some kind of positive aspects and some difficulties. The other motivation for which mathematicians and also educators like myself thought that it would be a good idea to use something new in the classroom to try to introduce this idea of proof to students is that if I had a pound for every time I heard in a common room my colleagues saying students can't understand proof, or students cannot do proofs, or students cannot write proofs, then I would be very rich. In order to be able to understand what the theorem prover can give to us, though, we need to unpack a little bit what we mean by student cannot understand proof, because this statement is quite general and it's also quite badly defined. So when I thought about this, I thought that there are at least 5 areas where a first-year undergraduate may find the difficulties, and this is not just my thoughts, but it's something that is kind of supported quite solidly by educational research. So the first area is an epistemological difficulty. So the students arrive at university from a schooling, at least in the UK, that doesn't really have this idea of proof. So students don't really know how is that we can say in the context of mathematics what is true or not. They don't do this at school. They don't kind of entertain this idea. School mathematics is very much procedural mathematics, where we apply arbitrarily difficult algorithms sometimes, but there isn't a lot of thinking about how can I establish the truthfulness of a result. And Geslange in her paper in 2016 calls this a first epistemological shock of a student's arrival at university. But it's not only that. So there are issues of proof comprehension. So how well do students understand the proof we present to them? There is some evidence in the research that students don't generally have a kind of overall understanding of the key ideas of the proof, but they usually at best check ideas line by line. So they check line by line whether one line is after the other, whether this makes sense, but they're not really able to tell what is the key idea. So if I had to do a map of this proof, what would that be? There are issues with proofwriting. Students and lecturers don't share the same ideas of what it means to write an academic style of proofwriting. And there is some quite really interesting research by Loy and Maya Ramos about this, where lecturers and students were presented with badly written proofs, and the results is that they didn't comment on the same things. Lecturers expecting something quite different than what the students did. Students are also not really very good at understanding whether proofs are correct or not. We never really ask them to do this. We always present them with proofs which are generally correct. And so when the students see a written proof, they kind of trust the authority. So this idea of critically appraise a proof and ask themselves the question, is this proof correct or not, is not really there. And this seems to me to be really important for mathematics. And then, of course, there is proof composition. So when a student is asked to write a proof that they haven't seen before, can they do this or not? And the answer, unfortunately, is not really often. And the problem are many, including how definitions are used in the context of proof, and how to start a proof, or how to partition the proof in all the various sub-goals that need to be solved. So if we think about these 5 areas of students' difficulties with proof, I think that it is not too difficult to think how theorem provers can help in alleviating some of these kind of problems. And we want to talk a little bit now at what price. So the first thing that is interesting is that a group of scholars in France have tried to understand a priori what these theorem provers can do, and they've taken 5, 6 interactive theorem provers, and they're putting them through kind of exercises to try to understand what were the characteristics that these theorem provers would flag. And the results are really interesting. The paper is quite long, so I'm only going to say that different theorem provers really try to hone different skills with undergraduate mathematics students, different mathematics capabilities. And it depends on what the teacher or the lecturer wants to do, that needs to guide the choice of which theorem provers to use in the classroom. But of course, studies like the one by Bartizia are very interesting because we don't all sit there and then do this kind of investigation every time we need to put a lecture together. So the first step is to try to understand what these theorem provers do, and some partial result is contained in this paper. Having done this a priori analysis, what are the directions for research that could be interesting to pursue? So the first part is using interactive theorem provers for teaching first year mathematics. So what does this mean? What I want these theorem provers to do? What are the questions I'm asking? I'm asking questions of whether these theorem provers make mathematics students better at writing proofs on pen and paper. So the idea is that I introduce them to this tool, but I still want them to write proofs in pen and paper. So we talk about transfer of skills. We want to talk about student engagement. So what happens when the students interact with the systems? And we also need to think about this idea of design principles for learning environments. And this is the work by Irene Garnello at Paderborn University, and Michael Liebendorfer is Irene Garnello's PhD study at the moment. This means that if I want to design a learning environment for my students, are there certain things I need to think about? What are the best ways of doing it, in a sense? The second part of a research direction that are currently going on is about teaching how to use and to be successful at using interactive theorem provers. So we have moved beyond, we have moved a little bit up the undergraduate degree, if you like. Now I'm in the third or in the fourth year, and I want to teach my students how to use interactive theorem provers. And so maybe they can use in the mathematicians' practice. And then again, we talk about design principles for learning environment. It is a different learning environment this time. But we also need to think about what knowledge do I want to kind of foster in this student. And this is the PhD of my student, Chiara Conclini. So regarding transferable skills, I am aware of two studies in this direction. The first one by, again, by Hannah and her team. They asked students, first year students, to go through lean proofs. And what I observed is that even putting students through this through using this system that may seem kind of very kind of fixed, this doesn't stifle students' creativity in trying to put together proofs, which could be a really good thing. Students often think that there is a one way of proving one thing, and then that's the way that we do it. This system seems to be encouraging students in thinking in a slightly different ways. And they also kind of found that using these systems, I think they use, I know they use Lean in their study, they can help with developing logical skills with students, and that can make them think a little bit about the proof structures. However, in this study, they didn't really kind of investigate whether the skills that they thought the students had developed with the interaction of Lean, whether this transferred to a proof on pen and paper. So the idea of all these studies, so the study by Hannah and her team, but also the study that myself and my collaborator Atina Thoma have done, is to see whether using theorem provers is making students better at writing proofs in pen and paper. The second study is relating to proof writing, really, and some aspect of the use of definitions within proofs. This is a study that we did in 2023 with my colleague Atina Thoma, and we gave this, we carried out a batch of task-based interviews with students in a lecture course where Lean was introduced, although not as a compulsory part. We gave the students these tasks, and then we asked them to write a proof of this task. The reason why we chose tasks like this in mathematics education is that we wanted the students to have a real new task, so something that they wouldn't have seen in class. I don't think that the definition of abundant number is a really interesting definition in mathematics. It's probably really not, but it's something that the students can understand quite quickly and can relate to other things that they know, but it's something that they will not have seen. And in this way, the proof task becomes really a novel proof task. So in some sense, some of the literature calls this problem-solving type of tasks. So we did all these task-based interviews. We scored the proofs that were produced. A colleague of ours who wasn't in the study scored them, and then we compared qualitatively proofs that were written, that were scored by our external person who scored the proofs at the same level of correctness. The reason why we did this is that we wanted to see whether we observe some skill that may have been acquired during using Lean in class or outside class, whether we could see some transfer in the writing of the students. What we found is that there was a big impact on mathematical writing with the students. So the students that had used Lean consistently in their writing, in their classes, used technical mathematical language and symbols much, much better than students who didn't. This is something that was observed already in 2019 by Jeremy Avigad when he was teaching his logic course with Lean. Interacting with Lean allowed students to understand much better the differences between technical mathematical language and programming language and natural language, which is the language we speak all the time. And this allowed them to be much better at writing proofs. So they were writing proofs in a way that a mathematician would be happy with, if you like. And this manifested in various ways. So, for example, it manifested in explicit statements regarding where certain mathematical objects belong. I've marked a lot of calculus course in exams in the past couple of years because of my job. And one of the things that I never see students introducing a mathematical object or variable or something and tell me what this is. So I will find something that has got to do with n, but I will never see let n be a natural number or something like this. This was quite frequent in students that used Lean. And also the proofs looked different. So they looked like a piece of text. The proof had words in it, had punctuation, you could read them, and this wasn't the case for other proofs. The structure of this proof was also different, and the proofs were structured with kind of in this idea of goals and sub-goals, and this is something that students have to do when they interact with Lean, of course. So this is the good stuff. The not so good stuff is that in this course, I think there were 300 students on roll, and I think 13 engaged with Lean. Lean was not a compulsory part of the course. And this is an issue for the people like myself and for my research, which I will talk about a little bit later. So the first thing that we observed is that we didn't really see students who had worked a lot with Lean using a lot of examples. And this is a problem because we know that examples are really important. A lot of the times when examples are used properly, they can help students understanding the general argument of a proof. So they can help students understanding what we say, the general in the particular. We didn't really see any of this in the interviews. So students who solved these tasks and that were used to work with Lean, they usually straight away started writing a proof very nicely and very kind of competently, but they didn't really think about examples very much at any point. And we thought that this may become an issue later on when proofs become more complex and they don't have this kind of idea of leveraging the examples that they know to try to understand what is going on with a certain statement. The other issue that we found is that some of the students really kind of try to use a very heavy logical machinery to write a proof on pen and paper, which was on the whole not really very difficult. And this caused some problems. However, the biggest problem that students found at that time, and I want to stress this was 2019, at that time they found this interface really unforgiving. They commented that even the students that were used to kind of programming tasks. Even students that knew, say, programming like Python, they found this programming language completely impossible to handle. It took a lot of time, and also one of the issues was that they couldn't really see at that point how a programming activity would relate to a piece of pure mathematics. And this is interesting because students are used to think about kind of using Python for mathematical modeling, for example, or writing kind of models of this sort. But at that time, and I stress this is now 7 years ago, they couldn't really see pure mathematics linked to something that looked like programming activity. Then we asked ourselves, okay, so suppose that I take a student and I get them through the natural number game. What will happen? Is this getting the students to understand a little bit more how to write proofs? The reason why we asked this ourselves is that we noticed since the natural number game was the first one in Lean 3 was put together by Kevin and one of his colleagues, that a lot of students spontaneously started to use this resource. So, for example, at Edinburgh University, we have a Lean Club, which now is run for, I think, 3 years, which is supported by the department in the sense that the head of school has agreed to buy pizza when they meet. But it's completely student-led, and these are students that have heard about Lean somewhere or another, done a little bit the natural number game, and they meet in the Lean Club to do various things that go from trying to formalize some simple results to trying to progress in the natural number game. So we asked ourselves whether this spontaneous engagement with Lean, completely unsupported from teaching and from pedagogical intervention, could be beneficial for students. So could we just say to the student, look, go and do the natural number game. This is going to be good for you. In order to do this, we put together 4 case studies. So we interviewed 4 students, I think about between 8 and 12 times each. So this was kind of longitudinal studies, like in that sense. And we kind of put the students through the natural number game. Again, this was a task-based interviews where the students were asked to talk aloud as they were kind of going through the game. We leveraged this thing called an instrumental framework by Trush. I'm not really going to say a lot about this, but this is kind of a theoretical tool that allows us to really understand what's going on when a human interacts with the tool. In fact, now this framework is used quite extensively to try to understand the interaction of students with generative AI in mathematics. So by using this framework, we were able to say that we could see, even in our small case studies, at least 2 completely different ways of approaching this tool. One that we argue was productive for learning mathematics, and the other one that we argue was not. So the one that we argue was productive for learning mathematics was the one of the students that he always referred to how they would write this proof on pen and paper, and then they taught how they would formalize it in Lean. We call this the constant comparison with written proof scheme. Forget about the word scheme, but this is the idea. And in this case, we could see a back and forth between the Lean proof and the pen and paper proof. And occasionally the students even rewrote the Lean proof because he didn't think that this was the way that he was happy with, because he wasn't showing enough of the proof that he would have written in pen and paper. So we argued that this could be a positive engagement with Lean. So Lean was really helping the students to understand when his pen and paper proofs were correct and when were not correct, what assumptions were made and were not. On the other hand, the other students was playing a game. So he was really using Lean if it was a computer game. It was very reliant on the feedback of Lean and on the goal state. And he went back and forth between the programming and the goal state all the time until the goal state was correct. And we called this, I played the Lean game scheme. The students told us quite happily that at times he was using tactics, not because he really knew what the tactic was doing, but because he knew that would have fixed that problem. Now, somebody has told me, a mathematician once told me, oh yeah, but this is the way I do mathematics and the way in which I use Lean. And I said, yes, but this is first-year students, so we would like them to learn how to do mathematics. And to be able to think about proofs, and then maybe they can start acting, kind of interacting with Lean this way. So this is telling us that we really need teaching resources, and then we really need well-structured Lean tasks and Lean resources that the students can use, structured with some pedagogical principles in the back and supported by an educational evaluation. What are the issues with this type of research? So at the moment, there are 73 courses listing that use Lean in the Lean community page, and 19 are tagged Intro to Proof. These courses sometimes, a little bit less now, but especially when we started, had the ITP as a voluntary part of the course. And this means that the uptake is very low, and it makes our life as researchers in mathematics education very different. What we usually do, this is again an example from my PhD students from another study, is we turn up in classes, or we put on learning environment things like, hello, I'm doing a student, please scan this code and come talk to me. This is what I would like you to talk to you about. But if you cannot recruit students, it's really quite difficult to carry on the studies. There is also another thing that we have noticed recently, and we have noticed that the picture is somehow what's shifting, meaning the picture of what our research is looking like. We are shifting our thinking from Lean as a resource in a first-year classroom to help students with the transition to proof, to I'm teaching Lean to, say, somewhat proficient mathematicians. What do these mathematicians, these students need to know in order to be able to be successful at using Lean? So I'm not now thinking I want to use Lean because this is going to show to the students they have to see the axiomatics, basics of mathematics, is help them with mathematical writing and so on. I'm now focusing on how can I teach students to be successful Lean users. And this is Chiara's, my PhD students' work. The first work I want to talk about is the work by Irene Garnello and Michael Liebendorf, and they are addressing this as well at the moment. So Irene is teaching a class on Lean, I think it's a series of, a small series of lectures. And she designed a prototype learning environment and has tested it with her students, trying to understand if I need to design another one, what design principle can I use? And the ideas that came are that the learning environment needs to provide a scaffold for the different levels of knowledge, needs to increase students' attention to the Lean outputs, and needs to guide students' attention to the connection between different representation of a proof. And this is because we know that obviously one thing is the proof which is written in Lean, and one thing is a proof which is written on pen and paper. This research is ongoing, and I'm looking forward to learn more about what Irene is doing at the INDROM conference in June this year. So, what are we? If we want to think about learning to write proofs in Lean, I need to know some mathematics, that would be desirable. I need to know how to program Lean. This would also be quite desirable. In the way, I need to have the backbones of Lean programming. And then I need to bring these two things together in order to write a proof with Lean. The question that we are trying to answer with the next bit of my slides is, what types of knowledge do I need in order to be able to successfully do what is in the bottom box here, so to write a proof in Lean? So if we want to talk about types of knowledge, the mathematics education has for a very long time talked about procedural knowledge, which is the knowledge of basically how to apply effectively and efficiently algorithms. So for example, if I need to do a very kind of a integral by substitution, do I know how to do this process? And this can be quite complex, and is not by no means undesirable. We need to have a lot of procedural knowledge in order to be able to be effective mathematicians. But the mathematics also talks about conceptual knowledge. So this is a bit more, we will see a bit more later what this is, but this is a bit more like understanding, what is a keen on understanding and on knowing what is going on. On the other hand, the programming education, the computer science education, in the context of programming talks about syntactic knowledge. So this is, do I know the programming language, for example? Conceptual knowledge, we'll talk a little bit more about this in a minute, and strategic knowledge, which talks to putting together the program and talking about loops and so on. The idea of using Lean is to put together these two types of knowledge, because I'm doing two things at the same time. I'm doing a mathematical proof, okay, not on pen and paper, maybe it's on Lean, but I need to know what to do. And I am also trying to program a functional language, which is Lean. So there is a very long kind of strand of research in what is conceptual knowledge in mathematics. It started a very long time ago. We worry about this because if you understand what students need in order to be able to be successful, then we can support them through teaching and through designing material and resources. One of the definitions that has had more popularity, if you like, is the one by Crooks and Alibal in 2014 that says that conceptual knowledge in proof is knowledge of objects, meanings, relationships, and their role in proving. So basically, in order to be able to talk about conceptual knowledge in mathematics, I need to know what are the mathematical objects that are involved in the piece of mathematics I'm looking for. And I really need to have the meaning of this object, what they are, what relationships do they have, how do they sit together with each other, and what is the role of each one of these objects in the proof that I'm going to write. There is some research that goes back many years now by Moore that, for example, shows that one of the difficulties when students write proof is that students cannot really use definitions in the context of a proof writing exercise. And if you like, this idea of conceptual knowledge talks back a little bit to this issue, to knowing the objects, the meanings, the relationship, and the role. For conceptual knowledge in programming, Quian and Leon in 2017 reviewed the relevant literature and kind of thought about this knowledge in terms of knowing how programming works, how loops operate, what occurs during an assignment, or why certain syntax is required. What we are doing with this study at the moment, we are trying to put together these two ideas and see how could these two ideas regarding conceptual knowledge can be put together so that I can say something about conceptual knowledge for using Lean. So what did we do? Well, mostly Chiara. She reviewed the literature on conceptual knowledge in computer science education and in mathematics education. It's quite a big job. So the definitions I showed before are only really the start of this, but there are very many perspectives in which this is looked at, including from starting from the ideas of what constitutes the proofs in mathematics education and all this. And the outcome at the moment is a tentative framework for understanding what conceptual knowledge in Lean is. And in the next slide, I'm going to show a table which is going to be horrible and very long to read, but then we are going to break it down and I'm going to explain what I mean. So this is the horrible table. And what this table does, tries to put together the aspects of conceptual knowledge that have been raised both in the programming language and in the proof education, if you like, language, and try to put them together to see what this means in Lean. So I'm going to take these rows one by one now, because this is just not really very nice to read, and try to talk, well, I guess quite quickly by now about these rows. So the first dimension of this conceptual knowledge is this idea of objects, constructs, and concepts. So we have seen that in the proof literature, conceptual knowledge always kind of concern knowledge of definitional axioms and theorems, examples, and in programming, knowledge of objects. Objects this time are different from the proof objects because these are things like variables, and constructs, and this time are things like loops. And so for Lean, we can talk about definition, theorems, and tactics. We always think about Lean working in tactic mode because somehow this is the most used mode in teaching, I think. And how this assumption and goal and hypothesis come together. So the crucial bit, once students can grasp these ideas of definition, theorems, assumptions, goals, is how they relate to each other. So this idea of conceptual knowledge is very much also not only thinking about the various objects in isolation, but how they interrelate and interact with each other. And this is the second line of my horrible table. And this is this idea of relationship and connections. So, for example, if I'm thinking about lean, I need to understand how the tactics play together, how the theorems play together, and how the explicit goal and sub-goal are visible in the interface. One issue that reminded me very much of what Kevin was saying before, that we are coming across also with this type of research, is that some of these things depend on the interface. So when there was a shift from Lean 3 to Lean 4, we had to really rethink a little bit about how, for example, the dynamics of the goals and the sub-goals and the goal states were visible in the interface, and where was the what was the best way to display the proof that have been written in Lean. So at the moment, I'm really hoping that there is nobody that's thinking about writing Lean 5, which is going to be very different from Lean 4. But I just wanted to say that some of these things will depend on the Lean interface that is used, but we assume that we are using Lean 4, and we assume that we're using Lean 4 in tactic states. So once we have this idea of dimension of objects and relationships, we need to understand the rules of the game, if you like. Now, the rules of the games are in two different ways. So mathematics plays by the rules of logic. I think we can agree on that. Programming plays by slightly different rules. So there's this idea of correctness, and there's this idea of programming principles. And in Lean, I need to both be careful to use logical coherence, but rigor and correctness, but I also need to use appropriate language, functional programming language, syntactics, style proof, and so on. So after I've talked about objects and principle and rules and connections, I really need to talk about language. So language is not something that is like secondary in any way to this thinking about a conceptual knowledge, but it's something that is very important. So Lean needs to bring together the functional programming language with, if you like, in a way, the proof language. So in terms of Lean language representations, we talk about this idea of functional programming, static style, type theory, and so on. And lastly, once I have kind of all these things in my mind, I need to have proper structure. So I need to be able to structure or organizing this. Oh, there is one dimension too many. This thing I want to write in Lean. So in proof structure, there have been quite a lot of exploration in the mathematics education literature how proofs at the undergraduate level are structured. So we talk about formal rhetorical state in the first part, where we declare all the objects that will play in the proof. Then we talk about the problem-solving activity, which is structured around goals and sub-goal. In programming, there is, in a way, a similar modularity in the design. So in Lean, we can put together tactic sequences in an incremental approach. So this is not easy to navigate. But I think it's something that is really quite interesting. I used to work a long time ago with somebody that every time I said, oh, I want to do this study, he was asking me, and why do you want to do that? What is it interesting about it? I think that this idea of trying to understand what is conceptual knowledge for Lean is really quite helpful for users so that they can connect the conceptual knowledge for mathematics and that for programming, and they can link these two activities and see that this programming activity actually is now part of pure mathematics. It helps people that design resources and researchers like myself to understand what is the best way to support the kind of fosterers of this type of knowledge. What are the resources that work better for supporting students in thinking about using Lean? And also helps a little bit, again, going back to the previous problem about what are the skills developed while using Lean that can be transferred on pen and paper. So this is, if you like, the motivation of a study like this. Interestingly, after we decided to do this study and Chiara submitted the paper to this conference, which was accepted, I'm very pleased to say, other people are starting to talk about conceptual knowledge and understanding. So already in 2008, Avigat proposed understanding as the possession of abilities. So if you think back about this terrible table that I shown before, thinking about conceptual knowledge is thinking about things that somebody can do, linking objects and doing this and doing that. So in a way, it's this possession of ability of being able to section proofs and goals and sub-goals, handle mathematical objects properly, and so on. In 2008, Avigat says that I will defend the fairly simple claim that ascriptions of understanding are best understood in terms of possession of certain abilities, and that it is an important philosophical task to try to characterize the relevant abilities in sufficient restricted context in which such ascriptions are made. In a way, the framework that we presented just now talks about abilities. So what somebody that has conceptual, that we think can think about conceptual knowledge, what is that they can do? More recently, that should be 2022, not 2002. Avigat wrote that our current preoccupation with conceptual methods could well give way to a more expansive view of mathematical understanding, one in which the computer plays a more central role. This isn't to say that we will then abandon the conceptual viewpoint entirely. What does this mean? Avigat thinks, after all his engagement with formal methods and from his perspective as a philosopher, that we will start thinking about conceptual knowledge in mathematics as such in a slightly different way, and this different way will be introduced by the use of computers. So, for this reason, we thought that thinking about conceptual knowledge seems to be timely because something is happening to the study of mathematics. I want to say that the question of whether thinking about conceptual knowledge in terms of being able to use an interactive theorem prover and doing mathematics will become the understanding in mathematics is a question that I would better leave to philosophers. We usually don't really answer philosophical questions, but what we do, we just collect more data. So what are we doing next for conceptual knowledge? The framework that you have seen at the moment, you have seen in my slide before, was something that we derived completely from existing empirical and theoretical literature. So we sat together, revised this literature, and trying to put together ideas that came from this literature. What my student Chiara is doing now, she's interviewing Lean users whom we think are capable Lean users. So these are not first-year students who are starting to use Lean. She recruited Lean users through the Zulip chat. And she's getting them to do tasks on a task-based interview setting to see, first of all, whether we can refine these categories that we have just talked about, and whether there is anything that we're missing. So is there anything that we cannot see from an analysis of the literature, but we can see in practice? So watch this space because she's still collecting data. So what is that we should really be doing next? I think that this idea of design and evaluation of teaching material and teaching tasks is really important. There is a lot of design and not a lot of evaluation, and I would like to see a little bit more of educational evaluation of teaching material. There is the investigation of strategic knowledge. What is this in mathematics? What is this in programming? And what is this in Lean? This is the other big thing. If you remember when we talked about the programming education, we talked about syntactic, strategic, and conceptual knowledge. So a next step once we done, or what we think we can do with conceptual knowledge, would be to think about strategic knowledge. And I think I'm really interested in, and this is a personal interest, in what way the way in which mathematicians do mathematics is changing. And is this changing the way in which students do mathematics? And will this impact on undergraduate mathematics teaching? And if this will impact, how? I don't have any answers to these questions, but maybe this is something that would be interesting to investigate. By talking to colleagues and giving talks and so on, I find that the mathematician speaker split between thinking that this is the future of mathematics and thinking that this is a fad that will go and mathematics will stay. I don't know where this is going, but it would be really, really interesting to see what happens to the practice of doing mathematics with the introduction of these systems. So that's my talk. I want to thank very much Chiara, who is working with Athena and myself at the University of Edinburgh, and my colleague Athena, who has done most of the studies with me. And thank you for listening.
Thank you very much, Paola. So now we've got time for questions. There are no questions yet in the Q&A, so I'll ask. So yeah, people do. Oh, there's a question here in the room.
Mine most likely got lost. I was somewhat surprised by the fact that students taught with Lean doesn't seem to use examples. Do you have an idea why that is the case?
I don't know. So we asked ourselves these questions at the time when we did the study, and I think that because my understanding is that the Lean interface is not necessarily conducive to say, oh, what about if I take this prime number, how does this decompose, or what about? And I think it was mostly because but with the interaction with Lean, they went directly into formalizing known statements rather than having to construct proofs at that time. I think that was the idea. So all the activity that the students were doing was to formalize statements. So at the time, they were formalizing basically undergraduate mathematics. And they had to do a lot of mathematical thinking in order to do that, of course, but they didn't have to think from scratch about, is this statement true or not? How do I understand how to prove it, if that makes sense? And I think that this transferred in the interviews that we did.
Yeah, thanks. That makes sense. I was surprised because for me, the motivation of using, in my case, Isabel for teaching is that it immediately allows students to test their definitions and lemmas before doing the proofs.
Mm-hmm. But this is why then we need this idea of educational resources, right? Because then we can guide the students' attention to, oh, actually, I want you to do this now, right? So go and have a test of something. Absolutely.
I mean, I was going to follow that up as well. I think this tells us more about the sorts of resources we design for students to use with Lean that focuses on the proof element and doesn't get the students doing examples, counterexamples within Lean itself, which it's perfectly capable of doing. But we need more focus on that in the resource design.
Yeah, exactly. And this is why the issue of resource design is really a big, big issue. And in the sense that it's something that we probably, as a community of mathematics education, people interested in this should pay more attention, right? Because resources guide the students' attention toward things. As your colleague was saying before, if I say to a student, okay, do this, and then go away and verify whether this is true, find examples and so on, then this kind of constructs a certain way of working with the student, right?
Yeah.
Okay, we do have another question, which is, do you have any thoughts on how to encourage students to adopt the compare with written proof scheme?
Oh, I think that again here education comes in. So we have just finished to work with two colleagues in the US who have taken over the course that Heather Macbeth used to teach. And as part of the assessment, the students are asked to write a proof in Lean and then the same proof on pen and paper, right? But the same, not the proof of the same statement. I'm not sure whether this is clear. And this transfer has been done constantly throughout the course, right? So this would be something that encourages them to think, I am doing this with Lean, but I also need to think about how we do this in pen and paper, and I would encourage this constant comparison. The students we were working with for that study, as I said, we just let them loose on the natural number game and say, go through the natural number game, what happens? These were first year students so they have done the first year. It was in the summer between the first and second year mathematics degree. So they knew a bit of mathematics and they had the ideas of what a proof should look like. and then they were making their way. So again, this structure, for example, of getting the students to think this is proof in Lean, how would you write this proof in pen and paper, or this is your proof in pen and paper, how would you formalize it in Lean, would be a useful avenue to go, I think.
Are there any more questions in the room?
I've posted one.
Okay. Yeah, maybe you can say it, yeah.
I've also posted it, but I'm struck when I use Lean about how much I use backward reasoning in tactics, a bit like your students. But when we teach proof on the board, we often focus almost exclusively on forward reasoning. Does that teach us something about how we might teach proof differently?
It might do. I mean, interestingly, there have been trials in mathematics education of try to teach proof differently from the expository argument that we usually do when we teach. None of this has been really taken on, and this idea of writing proofs on the board as we do at the moment has stayed for a very long time. But this idea of the thinking backwards may help students being a little bit better at putting proofs together. A lot of the time, students look at the statement and don't really know where they need to go, right?
Yeah.
Okay, great. And now we've got another couple of questions. How adaptable / translatable do you believe your research methods and results would be to other proof assistants?
So I think it depends a little bit on the structure of the proof assistant, right? So I don't think that our results are necessarily transferable to this category of a proof assistant, which I've described as proof assistants written for mathematics education, things like Educera or Lurch. They really work in quite different ways. There is one, which I can't remember now which one it is, which basically a lot of the time is a parsing problem. So you need to kind of slot bits of proofs into predetermined schemes. So this would be an unrelated activity from the activity that we have done with Lean. I think that things like, for example, ROC would probably transfer better. So within the basket of theorem provers that, if you like, work like Lean in a sense. So require you to write lines of programming and were written for research. They are probably generalizable, not for other theorem provers, I don't think. And of course, the scenarios with things like Lean verbose is completely different, because what the students do there, they actually write proofs nearly how they would write them in pen and paper.
Brilliant, thank you. So I've got another comment. It begins with a parenthetical statement. As a philosopher, I cannot help making a comment on understanding. Perhaps there isn't anything more philosophical about understanding than there is about proof. One view of what a proof is just anything whatever that convinces or should convince you of the theorem, if you understand the relevant background. Likewise, to understand a proof or other bit of mathematics is just to be able to do certain things with it, usually prove other things. This connection is one of the reasons that I would worry about automation. If it doesn't generate understanding, it arguably doesn't generate proofs, and vice versa.
Well, I have to say, I was terrified that there would be a philosopher in the room, because I am not a philosopher. As you have seen, my research is quite different. But there is a little part of me that agrees with this statement, and I kind of worry about formalization in the same way that I worry about about missing basic capability, if you like. So I agree with the idea that what is a proof is a social construct to some extent, right? So a lot of people talk about the proof being an argument that's accepted by the community of mathematicians and that kind of fulfills certain logic requirements and so on. I think that trying to expose students to tools like Lean, it is beneficial in that we keep them a little bit more on board on what is happening at the moment. I mean, we still teach 19th century mathematics, and a lot of the students don't really know much more kind of beyond 19th century mathematics. And this would help them a little bit to see something that is current at the moment, but I wouldn't go formalization full whack. I don't know how to explain it. I would keep the link with the kind of proof in pen and paper. the start. And then, of course, courses that want to teach Lean is a completely different kettle of fish, right? So this can be master courses or kind of advanced courses of students that want to learn Lean because of whatever, their future career, whatever. These are different things. But there are a lot of things that worry me a little bit about formalization and the advent of for-profit organizations into the pure mathematics arena. But it's another talk.
Oh, brilliant! Thanks, Paola. I think partly that question might have been about, well, as well as being about formalization, it was about automation too. I think the last sentence was, I would worry about automation. If it doesn't generate understanding, it arguably doesn't generate proofs, and vice versa.
Yeah, I mean, this is the idea that that we try to explain to the students that a proof needs also to some extent to explain to you what is happening, right? And a lot of very long automated proofs, I don't think they do that. So, but I think that we in a kind of at the level where I am with my research and with my students, we are very, very far away from like these very long automated proofs. So we always try to keep it grounded, if you like.
That assumes we know how to measure understanding independently of the proof, which is already an interesting philosophical question.
Yeah, and that, so perhaps I've got a question. So one of the issues, as you mentioned, is the difficulty of dealing with examples, and often because there will be something that seems completely obvious that you want to prove regarding your example, but which is really hard to prove in Lean. To a certain extent, could one just leave that obvious thing as a statement that we are just going to accept, or maybe you can get the AI to prove that obvious statement, and then you could focus on the human aspect of understanding more than the technical details.
Yeah, maybe. I mean, as I said, there are so many ways to do this at the moment. I'm not necessarily against using AI, maybe also in conjunction with Lean. I'm just a little bit worried about what this is going to do to the students' critical ability and to the students' understanding. So I'm a little bit like my philosopher colleague who just joined, who posted a comment earlier.
And Chiara is saying hello.
Yeah, Chiara is saying hello.
Not a question, but yeah, it's a statement. Any other? Well, we'll leave this open for a few more minutes, and then you'll be joining us at noon British Summer Time for the panel session. So we'll just leave it open for a bit longer. And if not, we'll be returning later on after a break for not Lean, the first non-Lean talk, which will be about Isabel. And we also have an opportunity to meet via Frame VR if anyone wants to have conversations in person. We also have the Zulip chat if people want to post thoughts and comments on Zulip. But I'll just wait for one more minute, and then well let's thank Paola now anyway.
Thank you.